Today we discussed JetBrains Health Challenge. It was a nice competition. I was very nervous about the difficulty because I thought last years we had like one problem in the end, which was very difficult, and it would kind of stop everyone to solve everything. And this time we had something different. We had two kind of difficult problem in the end, difficult in different ways, but they both are solvable. So I was expecting someone to solve all the problems very fast, but yeah, luckily it didn't happen. So everybody found something to stack. No, it wouldn't be end of the world. So if someone solved all the problem, it's not that big problem. It will just not look as beautiful as it is now. I think results looks amazing. Thank you for everyone who participated. Let's discuss the tasks. So the first task is very simple. Again, it's not very simple, so it's not trivial. Yeah. So you need to program some. You need to think on this problem. So what we have alternating schedule between two people. We have Alice and Bob, and they alternate doing something. Yes. And sometimes they make mistakes. So sometimes instead of having the opposite person, we have the same person next day. Yeah? And we have a list of these mistakes. So here we have mistakes in positions 4, 8, and 9. Yeah, like here you have in this, here you have it as an example. Yeah. And the question is to simulate this process and say who will do this thing how many times. Yeah. No. Again, I added this subtask just for everyone who okay, so just for everyone who's not sure how to solve this. So if n is small, you can just simulate the whole process. Yes, so you just go day by day and think if the day is special, you do the same person as before. If the day is not special, you do the opposite as before, and just simulate all the days, print the results, something like this. Yeah. Okay, but mostly everybody solved the full problem. So to do the full problem, you need to simulate kind of the process, but do it in a more clever way. Yes. So what we do, we have again, we have this sequence. Let's say like this: A B A, A B A B B B A B. And some days are special. Let's mark them. So this is special. This. So what you're doing is basically split everything into regular segments. Yeah. So all this sequence can be split into several regular segments. So here I have some regular segments. Here I have another regular segment. Here I have a very small regular segment. Here. So every time I make mistake, I start a new regular sequence. Yeah. Now it's easy to calculate what is the length of every regular segment, and it's kind of easy to find who is the first person. So let's for simplicity say that the first day is also strange. So like if I start from B here, yeah, in day 0. So every for every segment, I need to know the length of this segment and who is the first in this segment. Yeah. Then if segment has even length, then they both have half of it. If it's odd length, then one of them has +1. Yes, and it is the one who is the first during this segment. Yeah. So for every segment, you need to remember the length and who is the first, and then go to the next segment and update the result. Yeah. So so this is basically the full solution. Let me show you my code. Yeah. So this is my code for the first problem. I do it like this. So I basically make array of all special events. I count them from 0 because I like everything to start from 0. Yeah. I add one special event to the end. Okay, so here I'm doing it differently. So here I do a special event to the end here. Now every segment is something until the special event. Yeah. So every segment kind of stops. So this is not special in my case. So every segment stops before the next special event day. Yeah. So I add all the special days and add one more virtual special day in the end. Now I just have all the segments before the next special day. And here I just count all them. So I have k+1 segments. For each segment, I calculate length of the segment, and I see who will be the first person. So initially it was person 1. Now every time I change it like this. Yeah. So it's x plus length of the segment and plus 1. Yeah. Modulo 2. So x plus length of the segment will give me who is the last, plus 1 will give me this one. Yes. That's it. And I just add the result. So here I have special formula which counts number of days of Alice for Alice also. Yeah. Okay. So if x equals 1, then plus x will give me like rounded to the seal of the half. Yeah. If x is 0, then it's floor of the half. Okay, just small cheating formulas. But idea is really simple. So I look at this x, and I look at the length, calculate how many days will Alice do the job, yeah, and then move to the next segment, yeah. Then I calculate how many days, and all other days will be done by Bob, yeah. Yeah, so I don't need to calculate 2 values. You can calculate 2 values, but actually you need only 1. Second can be calculated in the end, like n minus this. So that's it. That's the first problem. Hope it was not very difficult for you. Okay. Have any questions? No. I'm here for G. Okay. We'll come to G. Okay. G is fun problem. We will get to it. Let's do it one by one. Okay. Let's go to problem B. How can I go problem like this? B. Problem B. Okay, so what we have in problem B, we have some increasing sequence of difficulties, and we need to remove one problem and then add one harder problem. Yeah, and we want to maximize total difficulty of all problems while keeping the set perfect. And here are all the definitions of the perfect set. Again, pretty straightforward problem, but you need to do it carefully. So what you need to do, so let's split the action into 2 actions. I need to remove one problem, then add some problem, yes? So let's try to remove problems one by one. 2 things may happen. So imagine you remove one problem. So you have these values A1, A2, A3, and so on. Let's say 5, 6, 7, yeah. So you have some 7 values, yeah. And imagine you take some values and remove it from the array. So like this value. There are 2 options basically. One option, if your set now is not perfect. It may happen if difference between these 2 problems is more than 2, yeah. So if A4 is greater than A2 multiplied by 2, then here you have 2 large gap, yeah. So you cannot keep it here. So you need to introduce new problem here, yeah, in this gap. And the difficulty of this problem will obviously be like 2A2, yeah. So this is the maximal possible problem you can put in this spot. Another option is when you took this problem away and this gap is small. So if A4, let's say, is less or equal than 2A2. Okay, write it different. It is the same way. Okay? Just wrote it in different formats. So if my sequence is good, then the best thing you can do is to introduce the most difficult possible problem. And you do it by introducing it here. So introduce new problem here with maximal possible difficulty. Yeah. So this new problem, like A8 in my case, yeah, new, will be equal to 2A7. Yeah. So you took this problem away and introduce a problem here. And okay, both these cases you can do in constant time. So you can just check all the problems, what happened if you remove them, and in constant time see what you can do. Yeah, then check all these cases and in linear time just find your solution. Pretty straightforward if you know what you're doing. So you need to understand, again, you need to understand problem statement, need to understand what we're asking you to do, and just carefully do it and do it ineffectively. So you do it effectively. So you do it in such a way that you have good time complexity. That's it. That's basically the whole problem. So let's look at my solution. So what I'm doing here, I calculate total sum. Why I need total sum? Because I want to, okay, That's how I calculate the answer. Okay. I calculate the total sum, initialize my result to total sum. If I don't change anything, I have this result. And then try to remove problems one by one. Starting, I can't remove problem 0. Problem 0 should stay there. Yeah? So I try to remove every problem from 1 to n minus 1 and check. So z is previous problem multiplied by 2. If I can do it and the gap is small, oh, I don't check if gap is small. Okay, so it's okay. So it's different implementation. Same idea, but different implementation. Here I just try to replace the problem in the same place. Yeah. So put new problem in the same place. So if I remove problem from position I and insert new problem in the same position, the difficulty of this problem can be maximum of this. So it can be either previous problem multiplied by 2 or the next problem. Yeah. So this is the maximal difficulty of the problem I can put in this position. Okay, so I check all these variants, and then I check all variants when I remove problem and put something in the end. So I remove the problem, check if it is still good. So difference between previous and next problem is small. Then I try to add new problem with this difficulty. Yeah. So last element multiplied by 2. And again take maximum of all these. So take maximum of all these variants, all these variants, yeah, output the maximum. Good, that's it. I like these problems. They are not that trivial. You need thinking in both this problem. You need to think. So if you solve at least these two problems, good for you. So not the most trivial problem actually, but they are kind of easy and approachable for everyone. So we don't need any special algorithms. Don't need any special anything. Just understand what's going on and carefully do it and try to do it fast. Yeah. So try to implement some fast algorithm to do what you need to do. Yeah. Good. Let's move next. Problem C. Problem C is combinatorics problem. So I usually try to put at least one combinatorics problem in a set, so you don't forget how to do combinatorics. So in this problem, we need to calculate some number of objects. Basically, what's happening in this problem? I have two permutations, and I have some prefix of these two permutations. So I have permutations of size 5. So I have 5 elements here and 5 elements here. Yeah. And I know only first 3 elements, and something here, and here only know first 3 elements. And I don't know these elements here. I'm curious what element can be in this position. Yeah. And I want to count how many different elements can be in this position, and I want to count them in two groups. I have first group of boring elements when I have the same element here. And I have group of interesting elements when I have different elements here, x here and y here. Okay, and you need to do it fast to get the full score. No. First, how to do it not. So if you don't looking for the fast solution, you can just check which elements are here. So I know, so like in this case, let's see. So I know the 1, 5, and 3 are here. Yeah. So what's left? 2 and 4. In this operation in some order. Same here. I have 5, 3, and 2 here. So 1 left and 4 left. Yeah. So in this position, you may have one of these 4 variants. Yeah. So you have 4 different variants, and one of them is in this position. Yeah. And you can just iterate through all of them and count how many boring ones, how many interesting ones, and get your 30 points. Perfectly normal. Yeah. But if you think a little bit more, you can easily see that actually it's easy to calculate without iterating over all n square values. Well, first, how to calculate total number of elements? So it's boring plus interesting. It's just number of total different configurations you can put in this position. And since here you have n minus k values, yeah, so you can put any of these values here, any of these values here. So you have n minus square, n minus k square total configurations you can put in this position. Now you just need to calculate number of boring configuration. Yes, so it's easy to calculate number of boring configuration, and then we'll just subtract get number of interesting configurations. So boring configurations are configurations when you have the same element on top and on bottom. Yes. And many ways to do it. Easiest way is to see that this is the element which is not used in both these permutations. So you just take all elements not used here, so not in here. So if no for here, so you take element which not occurs anywhere here in these two prefixes, and just count how many elements you have. And this is your number of boring elements you may have here. That's pretty much it. So you calculate number of elements you have in these prefixes. All the rest elements may create a boring pair. You have a number of boring pair. You have total number of pairs. You subtract, get number of interesting pairs. That's basically the solution. Let me show you them, please. So that's my solution. So okay, I do it like this. You don't need sets actually. So you can use sets because you don't. But actually you can do it with simple arrays. So you just mark all used elements. There are just n elements. You can mark all used elements and just iterate, check how many elements are unused. But you can use sets. It's easy to write. It's actually easy to read. Yeah. It has worse time complexity than just arrays, but you don't care that much. Yes. In this problem, you don't care about the most optimal solution. Yeah, it's okay. So this is number of boring elements. It's just n minus number of used. It's number of unused elements. And here is total number of elements minus number of boring elements. That's it. That's solution of problem C. Yes, let's see how many boring inserts. Yes, sorry, just got your text. Oh, good. Move next. Okay, next problem D. Problem D is actually surprisingly hard. I didn't expect it to be that hard for students, but many students skipped problem D. Some solve problem E and F and then just skip problem D. It's interesting. And here you see that some people skip problem E, some skip problem. So difficulty is very subjective term. So some people decide that problem F is much easier than problem D. You see. So problem D is the first problem which is actually not trivial. Let's see. So what we have in problem D? We have two arrays which satisfy these two properties. Why they satisfy these two properties? That's a good question. I was thinking of removing this from the problem statement, but decided to keep it just as it is because that's how the author first presented this problem. So I thought, okay, let's just keep this. The thing is, if you don't have these properties, then it's obviously impossible to build a sequence. So you need this property because every operation keeps the sum of elements. So sum of elements obviously must be the same. Yeah. And this property is also important because for every so it just tells you that every prefix sum of array R is not greater than prefix sum. And you can easily see that this property only increases the prefix sums. Yeah. So if you look at any prefix sums, okay, this is your array R. Yeah? So if you make plus x here and minus x here, then what happens to prefix sums? So these prefix sums are the same. These prefix sums are increased by x, and these prefix sums are the same. Yeah. So this operation only increases the prefix sums. Okay, so these two properties just guarantees that the answer exists. Okay, and actually, okay, so removing them from the problem statement would be fine. So I can just ask you to output -1 if next, but it's actually give you some hint of what's going on, and I decided so problem is not trivial itself, so it's fine to have just small hint here. Okay, but for someone it may be not give a hint, but just confusion. Okay, but yeah. Okay, so solution for this problem is like this. So let's look at the operation we can do. So imagine you have you have array R, array B, and you have some pair of elements. One of pair of elements is less. So here you have, I don't know, element 5, and here element 10. So it's less. And somewhere to the right, you have element which is greater. So like here you have 20, and here you have 13. Yeah. So the idea is to make one operation which eliminates one of these pairs. So you have two pairs, yes, of pairs, yeah. So you have two pairs of non-equal elements. So you have two indices, index I, index j, of non-equal elements. So in these two positions, Ri is not equals to Bi. Yeah. So what you can do? You can eliminate one of these pairs. So you can choose X as minimum of these two differences. So it's minimum of Bi minus Ri and Rj minus Bj. Yeah. So here the difference is 5. Here the difference is 7. So this difference is smaller. So let's take this difference and apply operation of this difference. Yeah. So if you apply operation of this difference, you have plus 5 here, you have minus 5 here. So this 5 becomes 10, this 20 becomes 15. Yeah. Now here you have equality. Yeah. This is very cool idea. The only problem is you cannot apply it anywhere because you need to keep your array non-decreasing. I actually received a lot of questions during the problem why this. So these examples are kind of good. So people get wrong answer on these examples and try to understand why they have wrong answer on these examples. Why here you can simplify it. Because you cannot. What I was talking? Yes. So you cannot just apply this operation because it may break this property. But it turns out sometimes you actually can apply. Let's see. So if you say R and array B, so if you have element less, then you have element greater. But all elements in the middle are equals. Then you can apply this operation. So in this case, I can actually always apply the operation and my array R will stay sorted. Now, why is it true? No, because you apply this operation again, you have plus X minus X. Let's say, for example, this is now equals. So this element is now equals. So here, after this operation, you have equality. Yeah. If you have equality, so this element, Ri plus 1, yeah, so Bi plus 1. So Ri now equals to Bi, but next element is also equals. So Ri plus 1 equals to Bi plus 1. Yeah, here. But array B is sorted. Yeah, less equal. Yeah. That means that my elements are also in sorted order. Yeah, so I don't break order here. Here I also don't break the order. You see why? No, again, because this element is okay, Rj minus 1, Rj, Bj minus 1, Bj. So Rj equals to Bj. Rj is greater than Bj. Yeah, so it must be also greater than R minus 1 because this is greater than this is greater or equal than this. So again, if I apply operation for these two pairs when all elements in the middle are equal, it will not break the sortingness of my array. Yeah, that's basically the whole idea. Now we just need to find a way to apply this operation. There are many ways to do it actually. Okay, many ways to do it. So we have some less, greater. Okay, so some elements less, some elements greater, less, greater, less, greater, something like this. Yeah. So what you can do, you can look at the sequence, take any elements next to each other. So if you have less and then greater and something equal, so let's look at all elements which are not equal. Yeah. And you take in this sequence of non-equal elements, you take two consecutive elements of different signs. So you have less and then greater. Yeah. And just make operation to this pair. One of these elements of this pair will be equal now. So you remove one of the elements and then continue. Simplest way to do it using stack. So you go from can you go from left to right? Yeah, you can go from left to right or right to left, doesn't matter. I go from right to left because that's how I thought. You can go left to right, actually it does the same thing. So you go like left to right and keep all elements which are less. So less, keep them. Then at some point you get greater, so you eliminate this pair. So one of these elements will be eliminated, let's say this element. Then you have the same, again, you have pair, and one of these will be eliminated. And you do it while you eliminate this pair. So basically you keep stack of one type, and when you have element, you take the last element from your stack and merge them. One of these elements will be eliminated, and just continue. Every time you remove one element, so you make up to n eliminations. That's basically it. Let's look at my code. Again, here I just read the data. Here I make so this will be my result. No, it's not a great make pair of pairs. I need 3 elements in my result. So not the best code style, but good enough. So here I keep this. So this is my stack. So I will go right to left, yes, and keep a stack of greater elements. So if R is greater than B, I put them to stack. Yeah. When I see element less than B, I take the last element from the stack and apply my operation to these 2 elements. So here I find this X, put it here, apply my operation. If I have equals now, I pop it from the stack. Yeah. That's it. That's the whole code. I'll just output the result. Now you see the solution is very simple. You just need simple stack, do it like this. But it is a smart solution. Yes, you need to carefully understand what's going on again and just see how you can do it. Again, I think the most difficult idea is you can actually apply the operation when all elements are in the middle are equals. It's not trivial idea, but okay, once you see this idea, everything else is kind of technical details. Do you have any questions? No, I'm just not sure if I hear you. Let me check. Okay, sometimes I set my output to my microphone because it has output for some reason, and I don't hear what you're saying for a whole lecture, but not today. Okay, let's go next. So if you don't have any questions, let's move to problem E. So now we have some, let's say, data structures problem. So here you need to implement data structure. So you need to implement data structure which contains some segments on line. So you have basically a line. On this line you have some segments from Li to Ri. And sometimes you have operation consolidate. Operation consolidate, you put it to some point X. It takes all the segments. So let's write them draw them as a segments. Okay. So let's say I have one segment, another segment, and some segment here. Let's see. So you take some value, some position X, take all the segments which include this position, and replace them all with one single segment like this. And that's it. So you just need to simulate this process. Pretty simple, yes? So, okay. A few things to notice. First thing to notice is when I consolidate some segments, I actually reduce number of segments. Yep. So here, if I took just three segments, I decrease total number of segments by 2. Yeah. And again, if you consolidate k segments, consolidate k segments, you decrease number of segments, by k-1. Yeah? What it basically means, it means that you have some, okay, if you know something about amortized data structure or amortized analysis, something like this, it may already give you some ideas of what's going on. You can do it just one by one. So if you find the way just to find these segments, so if you know these segments, yeah, if you just find these segments, you can just find them one by one. You take them one by one, calculate the leftmost left border, rightmost right border, just remove them from the set one by one, and add this extra segment back. And you can do it one by one because you cannot remove too many segments. Yes, you kind of every time you add one segment, so you cannot remove more than n segments. Yeah. So in total you remove up to n segments from your data structure. So the only thing you need to do is actually to build data structure which allows you to find segment that contains the given point. Yeah. So now the question is like this, actually. So you're given some set of segments. Yeah. So not given. So you have structure which contains some segments, and sometimes you take some point x, and when you take point x, you need to find all the segments that contain points x. Yeah. And you need to find them somehow one by one. Yeah. Okay, now next idea is kind of classical. So what do you mean by having the point x inside? So you have, so the segment contains the point if the left border is less or equal than x and the right border is greater or equal to x. Yeah. Okay. Okay. Basically you have two-dimensional request. So if you learn something about data structure, about like segment trees, stuff like this, basically we have kind of two-dimensional problem. You see? So if you think about every segment so as a point, okay, that's strange thought if you didn't do it before. So you can think about segment as a two-dimensional object. Yeah. So every segment have two coordinates, left coordinate and right coordinate. So you can represent segment as a point in two-dimensional space. Okay. And what we're doing here, we're looking for points. We take some value x, and we're looking for points with left border less than x, so it's to the left, and right border is greater than x. So we're looking for points in this section of the plane. Yeah. Okay. So again, if you build two-dimensional grid and make every segment as a point in this grid. Yeah. So what we're looking here, we're looking for points in this quadrant of this space of the two-dimensional space. See? Okay, so you can do it using some two-dimensional data structures. Quite possible. I'm not sure if it will fit in time limit. Okay, we don't have any intermediate groups here. But you actually don't need two-dimensional data structure. You need just one-dimensional data structure. Because you can apply the following trick. You can think about one of these values as the index in your segment tree. So now you have only one dimension. So basically, you represent one of these elements as index in your segment tree, and another value is value in your segment tree. Yeah. So in your segment tree, like imagine you have segment tree over these coordinates. Yeah. Then what you're looking for, you take this part of your segment tree, it's a segment, yeah, and look for elements greater or equal than x. So this is x, yeah. Yeah. So you take segment of L up to x, and inside this segment you look for elements greater or equal than x. Yeah. And again, that's something you can do using segment trees. So in the segment trees, you can take the segment and find all the values greater or equal than x. You just need to maintain segment for maximums. Yeah. So you maintain maximum value for each segment and basically traverse the tree. For each subtree, you check if you have anything inside. Again, if you okay, I will advertise myself again. So here is a nice course about segment trees. Let me just segment trees, segment trees. Yeah, this part one, I believe. So in this lesson, I discuss not all, but a lot of different problems about segment trees, and one of them actually to find. Okay, maybe I don't discuss this specific problem, but I discuss a lot of different variations of segment trees. I think this one I also said versions, nested segments, in segment. So that's basically it. So you have nested segments, intersecting segments. So if you don't, if you didn't solve problems like this before, and all this is new for you, just go there and just solve all the problems in this lesson. It will help you a lot in the segment trees. Segment tree is one of the most important data structure in competitive programming. Yeah. So just learn how to do it without any thinking, and you will be great. Okay, so that's basically it. So what I will do, I will take all left borders, compress them, because I have large coordinates, yes. So I will, instead of having different left borders, I will just compress them to numbers from 1 to n. And then just maintain this. So for every left border, I will remember that. Okay, so let's think about it without two-dimensional picture. What I'm doing, for each left border, I remember the right border of this segment. Yeah. And now in a segment tree, I will do like this. I will take all left borders in this region, yes, and find the segments with left border here and right borders greater or equal x. So I will look for values greater or equal x in this side of my segment tree. Yeah, and every value will be a segment which contains element x. That's it. Let's look for my code. Let me open it. So, it's kind of long, you see. Okay, 120 lines. No, because I have, look here, I use my normal segment tree, which I normally use in the contests. I just took it from my library, so you can do it more compact, but I don't. So this variation of segment tree, which calculate maximums and allows you to find element greater or equal than x. Let's see how I do it. I calculate maximum for each subtree. This just set the value, just normal way. Here I find, okay, this recursive function find elements greater or equal x in a segment from L to R. Yeah. It returns special value not found if it didn't found anything. Yeah. So I do it like this. If I'm out of the segment, I return nothing. If maximum is less than x, I return nothing. It means I don't have any element greater than x. Yeah. If I am in the leaf, just return this leaf. No, I return pair index plus the element. So I don't have two requests. Just okay. Yeah. Here I look in the left subtree. If I don't find anything, if I didn't find anything in the left subtree, then I go to the right subtree. And so this function in log n time finds me any element, no, actually leftmost element greater or equal than x. No, that's it. Just building segment tree. Nothing interesting here. Okay, so this is now the intellectual part. So this is just normal segment tree. Nothing interesting there actually. So here, what I'm doing here, I compress the coordinates somewhere here. Here, I must compress the coordinates. Okay, okay. Complicated code. You can do it better than me. So what I'm doing here, I try to put all my segments into this array and then sort it by the left border. And if left border is the same, I sort them by the right border because I kind of want so if, or it doesn't matter. Yeah, probably doesn't matter. Yeah, probably doesn't, in this problem probably doesn't matter. So here I take the okay. So if t equals 1, I just read the borders and put them here. If t equals 2, I put it here and use the second value as a marker that this is correct. Not a nice code. So if this value is equal to int max, it means I have a consolidation query. Yeah. And here I just put the index because I need to output them. Yeah. Okay, so here I sort them all, go left to right, and just p. Okay. So for every segment, I want to know its position in my segment tree. So that's what I'm doing here. Okay, so I sort all the segments by the left border, sort them, yeah, and then assign to each segment its position in the sorted order. And I put them both segments and my queries. Okay. Very complicated code. Yes, and my query will be after my queries because here I have int max. Okay. No, it works. It's just okay. You can find better way to do it, I believe, but it's actually good enough. So here I build segment tree and just go for my queries one by one. Take the element. So x is the okay. That's complicated code. So I take I. For this I take pi. It's my position in sorted order. Then I take a of this and first. So it's okay. So it's the left border of my segment x. Okay. No, it's not the left. It's pair. Okay, it's pair of left and right border. If it's int max, it means I have a query of consolidation. Okay, I'm not very proud of this code, but it's actually good enough for the competitive programming. It's good enough. So arrays will be my result number of segments. Okay, and here I will do following. I will find all the segments I need to consolidate one by one, and I will count number of them and find the new left and right border. So new left border will be here. It's just the first segment I find because I find them left to right because how this function works. Okay, not great. And right will be maximum of them. Okay, you can calculate left as minimum of them to make the code more clear, but okay. But because I'm going left to right, you can do it like this. Okay. So here I find a new segment. If I didn't find a segment, I break. If I find segment, I update my left, update my right. I remove the segment from the segment tree. I remove it by putting int min to this position. Yeah. So my segment is for maximum. So putting int min basically puts some neutral value in this position. Basically, I remove segment from my segment tree. Yeah. Increase res. If res is neutral, then I introduce new segment to my segment tree. No, that's it. I'm not sure if you can do it just using sets. I don't know how to solve this problem without any segment trees, but segment tree is simple data structure. So if you not familiar with segment trees, not that great in the segment trees, just learn how to do it. So segment tree is very simple and very useful data structure. Highly recommend, highly recommend. Do you have any questions? No? What if L coordinates for some segments are the same? We only remember the maximum value of this. Yes. If segments have the same left value, I just sort them here and assign them different values. So I don't compress coordinates like I usually do. Usually when you compress coordinates, you sort all different coordinates. So what you usually do? What is coordinates compression? So you have some segments and they have different coordinates. So one is coordinate from 1 minus 5 to 10, another like from 2 to 20, and another like also from 2 to 8. Yes. So normally what you do, you take all the ends of all the segments, put them in an array, sort it 2, 2, 8, 10, 20, and then just remove duplicates. And then you assign, so assign 0, 1, 2, 3, 4. Yeah. So you assign to each coordinate one of these compressed values. That's how you normally do path compression. Here I do it differently. I don't remove duplicates. So I will do it like this. 2. So I will assign just different coordinates to these two elements because I can. So I will basically move one of these borders epsilon to the left. So one of these borders will be epsilon to the left. So it will be not 2, but 2 minus epsilon. So it doesn't change anything in the rest, but now all the segments have different coordinates. So this coordinate is 1, this coordinate is 1, this coordinate is 2. And this kind of eliminates all the problem with the same left borders. Yeah. So let's hear how I do it. So here I just read all the segments, just sort them. And again, usually here you have something like unique and to remove all duplicates. Yeah. But I don't do it. I just keep all coordinates and assign my values like this. Yeah. I only make sure that if I have some segments from the same location and I have a query in this point, then my query is to the right from. So I move them all segments to the left and queries after all the segments. So I have like this, and then the query. Yeah. So all the left borders are to the left from the query. And I achieve this by putting this int max. This is why I have this int max, not int min in this position. Yes, you see. So it after all the left borders. Yeah. Okay. That's actually the tricky implementation part. Yes. I believe it's the easiest way to do it actually. But if you know some easier solution, tell me. No, you can, for example, you can maintain for each element, you can maintain set of right borders, but it's much more complicated. And then you have set inside segment trees. Not great. You can maintain not sets, but sorted lists. So in each, for each left border, you can maintain a sorted list because you only remove elements right. Then you need to insert in the sorted list. Yeah, no. Much more complicated. Okay, so that's problem E. Let's move next. Next problem F. Okay, many people told me the problem F is actually easier. I don't quite understand why it's so easy. So maybe modern people just better in this because of how code forces work on something like this. So people just more skilled in problems of this type. So formulas like this doesn't scare people anymore. Okay, when I first read this problem, I look at this formula, I think, okay, that should be some crazy math problem, something like this. So I don't like this. But modern students just read this formula and think, okay, everything good, so we will just do it. Good for you, good for you. What's happening in this problem? So we need to so we have a sequence, we have actually permutation. It's actually not that important, this permutation. We just make this to confuse you. The important thing that you have small, so all elements of the sequence are kind of small, up to n, so we can factorize them. But again, so you have permutation, and you want to find the segment. So you have p, and you want to find the segment number of segments, so that if you look any elements of the minimal element which is not a divisor, so minimal x not which is not a divisor, okay, not a divisor equals k. Now let's just translate this to normal language. So what's happening here? I'm looking for a segment such that all the numbers from 1 to k minus 1 are divisors. Divisors of something in this segment, yeah? And k is not a divisor. Not divisor. Okay, let's talk about second property first. So k shouldn't be divisor of any elements in this segment. So what you can do, you can take your segment, find all elements divisible by k. Yeah. And now you kind of split your problem into small problems. So you need to solve your problem. So none of these elements can be in your segment. So you kind of split your problems into several ones. So you need to find segments here, 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 here. Now, two more tricky part. We need to make sure that all numbers from 1 to k minus 1 are divisors. No, many ways to it. The important property case, let's go to it. Important observation you need to have about the about numbers in general, that numbers normally have small number of divisors. So number of divisors of a number like in this up to 10 power 5 is really small. So like hundreds of divisors. So you can just find all the divisors for all numbers in your segment. Okay. Now this fact is like more known to people, but okay, if it's the first time you get this fact, it's not a problem. So what we can do, we can just find all divisors for all numbers. Now, when we find all the divisors for all numbers, what can we do? We can basically go left to right, and for every divisor from 1 to k minus 1, keep the track of the last time we see this divisor. So for every divisor, we keep the track of the last time we saw this divisor. Yeah. So imagine I read my array from up to this point. Yeah. Now I'm looking for the segment which contains all the divisors. So if for every divisor I find the rightmost position, yeah, then I just need to find the minimal out of all these positions. So this is the minimal segment I need to have. So this is the minimal length of the segment starting from this point that contains all the divisors. Yeah. So what I will do, I will keep track of every divisor and find the last time I see this divisor. Yeah. And then I need data structure which allows me to find the minimum. Here, if you actually have some set of priority, you get time limits, I believe. Okay, we didn't add special subtask here because we have no time for doing it. Okay, so you need find a way to find the minimum in this element. But you don't need sets actually here. You can just basically have 2 pointers. Basically, you just make 2 pointers. So you take this right pointer and move it to the right here, and take this left pointer. Left pointer will go to the leftmost position when I have all the divisors. Yeah, and every time you move the right pointer, these pointers move to the right. So this pointer also moves to the right. So everything moves to the right. Yeah. So this is how you do it basically in linear time. Okay, not linear. Linear multiplied by number of divisors. But number of divisors is small. Okay, hope it's clear enough. So let's read code. Okay, so this code, it's pretty short. You see, it's like 60 lines of code. Easy. So what we're doing here? So here I find all the divisors of all the numbers. Very simple code. I take the divisor. I only care about divisors up to k. So I take the divisor and then find all its multiples and add my divisor to the list for this multiple. See, very simple code. In n log n time, find as n log n time, find all the divisors of all the numbers. Very simple. Now here, okay, what I'm doing here, I maintain pointer to the last number divisible by k. Yes, and I maintain, so here, so this is the last time I saw every divisor from 1 to k minus 1. And okay, this thing I use to move the left pointer. So I maintain for every position number of pointers points to this position. Something like this. So I start from -1, put it to -1. And so all last -1. Okay. Yeah, good. So what I'm doing here, so I take the next element, see if it is divisible by k. I just update my border of numbers divisible by k and go next. I basically start a new block of elements not divisible by k. If it's not divisible by k, I look at all its divisors and update the pointer. Yeah. So again, I move the pointer to the next position and update this counter. So now one less counter points here, one more counter points here. Now I move the left pointer. Okay, it's called T for some reason. Okay. So T is this left pointer, points to the leftmost of all divisors. So I see if nobody points here, then I move to the right. So I move to the last element, which is, so it is leftmost position of some divisor. So I cannot move any further to the right. Yeah. So if it is in my segment, so if it is in my block, if it is after my last k, I add this number of segments to the result. That's it. Pretty simple actually, if you think about it. But so okay, this part is intellectual, that you need to keep track of the last position of each divisors. But yes, this part is intellectual. Good. Two problems left. Let's go. Okay, now we have two hard problems. One of them is kind of, you need to have some idea here, so it's more of a mathematical problem. And another problem is more like technical realization problem, something like this. Yeah. Problem G, genius problem actually. Very simple, but very genius. Yeah. So what's happening? We have some sequence. Let's have some sequence. 1 1 0 1 0 1. and we can make the operation. The operation is like this. We take all the prefixes and calculate XOR of these prefixes, starting from XOR 2. So XOR of 2 elements is 1, then we add 1, 0, 1, 1, 0, 0, 1. Yeah. So I calculate, okay, so what happened? This XOR is 1, this XOR is 0, this XOR is 1, and so on. Yeah. Basically, we deal like prefix sums, but not sums, but XORs. Yeah. So we prefix XORs of this array, starting from size 2. Or you can do the same from right to left. So you can take 1, so you start from here. So you have 1, then you have 0, 0, 1, 0, 0, 1. Yeah. Different array. Yeah. So from this state, you can go either to this state or to this state. And the question is to make the sequence of operations such that in the end you have single one. Okay. Okay, how to approach problems like this? How do I usually approach problems like this? What I think first? I think about situations when it's impossible. So when someone asks you to construct some object, like here, construct sequence of moves, which takes you this. You think, okay, when is it possible? Yeah. So let's think when it's impossible. Well, for example, if all zeros looks like impossible. Yeah. You do anything, you have again zeros. So this is definitely impossible. That's something. Are there any other impossible cases, do you think? Okay, so you kind of want to eliminate all impossible objects and then think, is it possible for everything else, and why is it possible for everything else? That's kind of thing. So again, you want to make some so for some objects you can present a construction. How do you do it? Yes, and for some it is impossible. Yeah. So you kind of want to draw this border, between which is possible and you know how to do it, and which is impossible and you can prove it is impossible. Yeah. So you want to find this border between these elements. Yeah. Okay. It's hard to explain. So that's what I'm doing here. I'm trying to find this border. So I want to find all the impossible elements. Okay. So all zeros definitely impossible. Let's find something more interesting. Yeah. For example, 1, 1. I can do anything and get 0. I get 0, I get 0, also impossible. You think, okay, that's more interesting. Yes. Can I do something, some sequence of 3 elements, which creates 1, 1? You think I can actually. So for example, sequence 0, 1, 0. Yeah. If you go from any direction, it will give you 1, 1. Then you think again. You think, okay, can I make something which will give me 1, 0, 1? Okay, if I have 0, then I have some equal elements here. So I have, for example, some x. Yes. Then I have 1. So I have some different element here. So some y. Then I have 0, I have 1. Okay, so I'm looking for something like this. Okay, let's check. So if I have 0, 0, 1, 1. Yeah. If I go left to right, yes, I get 0, 1, 0. If I go right to left, I get 0. See? 0, 0. No. Yes. In both cases, I have impossible. Yes, you see? So any situation like this will also be impossible. Interesting, yes? So now you go one step forward. Okay, which combinations of 5 digits will give me this? Now you see, okay, so if 2 elements so you have some 5 elements, 1, 2, 3, 4, 5. If these 2 elements are equal, it means that, so here I must have 0. Yeah, because okay, so this x is sum of this prefix, this is sum of this prefix, so this element must be 0, and this element are equal, so this element must be 0. Yeah, and if I go from right to left, I must have the same picture, so this element must also be 0. Yeah. So you see, if you have any sequence like this, it also should be impossible. Yeah, because every time you have something like this, it will do something like this, and this will do like this, and this will do this, and this will do 0. Yeah. So you kind of trying to construct all impossible objects here and see how they structured. And again, if okay, after this, it's actually already kind of clear. So impossible objects look like this. You either have a sequence of odd size with every second element 0. So you have zeros, like say something. Okay, let's say something. So dot is something, 0 something 0 something 0. Yeah. So for odd length you have object like this, and for even size you have object like this. You have something like AA, BB, CC, DD. So it have pairs of equal elements for even length. Okay. Okay. So at this point you stop and think, okay, is it everything? So is it all? So are there any other impossible objects? And you can do it by stress testing actually also. So you can just stress test all different combinations of small size and just generate all impossible combinations. Also doable. So you can do it like for sizes up to, I don't know, 20 easily. And if you look at all sequence of size up to 20, it's easy to find the patterns. Okay. But okay, imagine that you tried a lot and didn't find any other group. So you think, okay, maybe all other objects are actually possible. No, let's see why. Okay, let's see if I have something not like this. So if I have even group, but some element, so I have, okay, let's say 0 something, but here I have 1. So if I have some 1 in the middle of my even length, let's try to apply some operation. Yeah. So I will apply operation on prefixes, for example. So I have prefix like this, some element A, yeah, and this again A. Then I have something, some B, and I have B, and I have not B. Let's say not B like this. And then I have C and C. Yeah. So I have configuration of odd size, of even size, which is also not impossible. Yeah. By my hypothesis. So I have a hypothesis that only these configurations give me impossible. Yeah. No, you can manually check it for sizes 1 and 2, for example. For size 1, yes, 0 is impossible, 1 is possible. For size 2, yes, 1, 1 is impossible, 0, 0 is impossible, 1, 0 is possible, 0, 1 is possible. Yeah. So for sizes 1 and 2, it works. So just continue. Now you see that if I have at least 1 here, so if not all these positions are zeros, if I have 1, then this 1 will create pair of non-equal elements here. Now, if I have something like this, if I have A, B, let's say not B, C, then you actually can do if you do any operation, then you will have here you have so this operation will be 1. So I have I have this. I have something. I have 0. Then I have something, and then I will have 1 here. So when I move from this prefix to this prefix, You see, I will have 1. Yeah, so again, so if you have non-impossible position, you can move to another non-impossible position and kind of reduce your problem to a smaller one. Okay. Okay, now let's move to the solution. The solution is to do the operations without moving to impossible state. Yeah, you can actually accidentally move to impossible state from possible. For example, if you have something like this. Yeah, so if you have something like this, if you calculate value for prefixes, you have 1, 1. So you don't do it like this. Yeah, so if you have 1 in the beginning, so if you have here, if the first element is 1, you always do operation on suffixes, not on prefixes. And if you have 1 here, you only do operation on prefixes, not on suffixes. That's basically the only trick you need to understand. Yeah. So if you have 1 in the middle, you can do any operation. If you have 1 in the beginning or in the end, you just do operation in this direction. So you don't destroy this one. Okay. Okay, you can implement this and get 25 points, actually 35 points. So to get 35 points, you actually need to implement carefully this and just try not to move in any impossible state. Yeah. To do a full solution, you actually need to do it more carefully. So you need to do without simulating the whole process. The problem is you cannot simulate the whole process. It's actually fun how the checker works, because checker actually simulates the whole process, but very effectively. So that's why we have checker for this problem. So checker works in n square time, but in very optimized. Maybe you also can solve the problem in n square time if you do it really careful. But I didn't find any. So the only person who solved it in incorrect way, actually. Let's do it like this. So imagine you have, so if you have even size, so you cannot do anything. So if even size, make operation. Even size, just make one operation, any operation. Now we have odd size. So let's find the first element which is not 0. So in the odd position, which is not 0, yeah? 1. Something. Yeah. So let's find the leftmost one in odd position. Let's try to keep it. Try not to break it. Okay. How you do it? How you do it? Yes. Do it like this. So you first do operation on suffixes. Okay. So when you do operation on suffixes, then here you have some different elements, you see? So because it's 1. So you have some x and not x. And here you have 3 pairs of equal elements. You have some AA, BB, CC. Yeah? And something there. So it's operation 2. Now let's apply operation 1. What will happen? This AA becomes 0, then I have something 0, then I have something 0, then I have something 1. You see, this prefix is the same basically. So these elements will be different, it doesn't matter. What's matter is that this one stays in the same place. So you make operation 2, operation 1, this one stays in the same position. And you can do this until, but the length decreases. So I basically removed the last 2 elements of this sequence, yeah? Keeping this prefix the same. And you do this until this element 1 is the last one. And when you have this sequence, you just make 1, 1, 1. until the end. In the end, you will have 1. That's the full solution. So you find if your sequence has even size, you make a single operation and reduce problem to odd size. If you have odd size, you find the leftmost one in odd position, then do some pairs to 1 until this element is the last one, and then make some sequence of ones until you have 1 in the end. That's the full solution. Again, very genius problem. So it's not just like implement some data structure or, you know, construct something. So here you just need to notice some things, and basically it's basically a research problem. Yes, so you have some objects, you need to research what's happening. Okay, so that's solution. So if size is even, you make single operation, continue. If size is odd, okay, it's not, it's a different approach, but it's kind of doing the same things. Okay, so here I'm looking for this one in odd position. Yes, so if I have 1 in this position, I keep it. If not, I make operations 1 1, basically remove element from the left. Okay, this problem G. Last problem. Supposed to be the hard problem, but it turns out problem G was actually harder. So we have 5 people solving the last problem and only 1 solving problem G. Okay, so problem H. So we have, okay, so what we have? We have some teams solving some problems, some problems, and we need to calculate some special value. So we for each solved problem, we count number of other problems which not solved by this team before, but have more solved. Okay, solved by more number of teams before. Yeah, so like, do we have any example here? Okay, let's look at this. So here for 1, 2, 3, 4. So for this solved, the suspicion is 1 because problem 4 was already solved more. So problems 4 already solved by 2 teams, but problem 3 is also only solved by 1 team. Yeah. So when this team solved problem 3, it has suspiciousness of 1 because there is another problem not solved by this team, but solved by more number of teams. Okay. And the question is to calculate this number. Okay, let's go. So if we just remove the second constraint, so if we remove the second constraint, so we not, the problem is actually surprisingly easy. Yeah. So we look at the problem, look how many solves does it have. Yeah. And we need to, so if we sort all problems by number of solves, so for each number of solves, like 0. So if we see how many people, how many teams solve the problem, yeah, and for each number of teams, we calculate number of problems solved by this many teams. Okay, now it sounds more complicated actually than it is. Okay, we have, okay, let's have scoreboard. Yes, so I have 3 problems, A, B, and C. Yeah, so I will give them names. Problems, yes, and these problems like this. Yeah, so I have 2 problems solved by only 1 team, 2 problems, and 1 problem solved by 3 teams. Yeah, 0. So I will create an array like this. See, now if someone solves problem A here, then problem A now solved by 1 team. I need to find number of problems solved by more than 1 team. It's just suffix sum, so I need sum of all these elements. Yeah. And it's actually easy to see that you can maintain suffix sums. Yeah. So what's happening to this array? Sometimes you move the element one position to the right. Yeah. Okay, let's solve it. So I have this, but after operation, I will after I solve this problem, I will move this element to the right. So I'll have 1 0 or 0 1 1 1 0. Yeah. So if you see how the suffix sum changes, suffix sums were like this. I have 0 0 0 1 1 3 0. Yeah. Before I make update. But after I make update this, I just make this sum to 2. So every time you solve the problem, you update single element in your suffix sums. So it's very easy to keep this array of suffix sums. Yeah. Okay. Now, again, if I don't have this constraint, it's very easy problem actually. So every time you solve the problem, you look how many people solve problem now, go to this suffix sum array, and take this element. Yeah, this element equals to this sum. Easy, easy. The problem is that I only care about problems not solved by this team. Yeah. Okay, and now you think, okay, what can I do? Can I do any data structures I know? And okay, if you experienced enough and you see 3 seconds, you may already think, okay, this smells like some square root decomposition. And it actually is. So you actually need to apply some kind of square root decomposition. I believe there are many ways to do it. The way we did it is like this. Let's split all the teams into 2 groups. Teams who solves a lot of problem and teams who solve small number of problems. And the trick is that in total, all the teams solve like 2 and 5 problems. So it's impossible that a lot of teams solve a lot of problems. Yeah. So if you keep the group of teams who solve a lot of problems, that group will be small. Yeah. Now, if teams solve small number of problems, then we can just subtract the problems we don't need from this sum. So we can get this sum, this suffix sum, yeah, and just subtract the problems we already solved, just one by one. Take all the problems, subtract them, easy. If the team solve a lot of problems, we can kind of keep the same array for this. So for each, so there are not that many teams that solve a lot of problems, yeah. So we can kind of, for each team that solves a lot of problems, we can maintain the same array of suffix sums. The only problem, it actually changes a lot. So because of every time you solve the problem, you need to make update to the suffix of this suffix sum. You kind of remove problem from the suffix array, or from the suffix sums. Yes. And you might need to make a lot of changes in this suffix sum array. So what we'll do instead, that for every large team, for every team that solves a lot of problems, we only keep this suffix sum array for a small number of here. Only keep a prefix of this small. Yeah. So we keep the suffix sums only for problems which solved by small number of teams. Yeah. Okay. Hope it makes sense. So again, we have small number of teams who solve a lot of problems. Then for every of these like fat, okay, it's like you have large teams and small teams. Yeah. For every large team, you maintain this suffix sum array, but you cannot do it the whole array because you not able to update it every time. Yeah. So you keep only small prefix of this array. So you keep these arrays only for large teams and for problems solved by small number of teams. Okay. And then for problem solved again. Now problems solved by a lot of teams. Again, there are small number of problems like this, so you can calculate them separately. Okay, you will. Yeah, I will show you the code. It makes much more sense when you look at the code. Let me show you the code. Code actually explains much better. See, so here I make just constant. So I just pick some constant close to square root. You can adjust it, make it 500, let's say so, and see which constant give you better result. Here, so I put some large teams here and some large problems here. So large team is some team who solved at least C problems. Yes, and C again, C is 1000, and I have in total, I have two. So 2 plus 5 divided by 1000, like 20,000 large teams. So I might have up to 20,000 large teams. Yeah. Okay, let's put in this array. Same for problems. I look at all problems, see how many people solve this problem. If a lot of people solve this problem, I put it in separate array. Yeah, and again, I have some small number of very large solved teams, solved problems. And now I just go with, so here, solved by at least, yes. So this is my suffix array, or suffix sum array. So solved by at least, okay, very mnemonic name. Yeah. So initially, everybody goes to the first cell, and then I will move them to the right. And this is the same array, but for every large team. Okay, just initiate. Okay, so see, so here I calculate. So first I calculate this number. So this number is just, again, it's the answer without constraint of problems unsolved. Just total number of problems which have solved more than this problem. Oh no, this part. Yeah. So this is how many people solve this problem, and this is how many other problems solved by more number of teams than me, by greater number of teams. Okay, got it. So this is my suffix sum. Now, if my team is not large, if my team didn't solve a lot of problems, then I just take all problems solved by my teams, yeah, and just subtract if they counted. Just make this correction, yeah, just brute force. But because it didn't solve a lot of problems, I can do brute force in 1000 operations, no more than 1000 here. Now, if my team is large, it solved a lot of problems, then if my team is large and the problem is large, okay, then I only care about large problems, yes, because only they are counted in this sum. So I look at all large problems, yes, and again make this correction. Good. Now, finally, if I have a large team and a small problem, then all this is calculated in this suffix sum for my large team. So for every large team, I have this suffix sum only for small problems. So I go there and calculate. That's it. Now I need to update. So I update the total suffix sum. Now I update every large team. Yeah, like a small number of large teams. I can just update all of them. And again, here, yeah, just okay. Just update this. Okay, this that's boring. Okay, just update this. Okay, so this is interesting update. So this is just update all the arrays, and here I update all the large teams. Yes, because if I solved some small problem, I need to update all the large teams. Okay. Yes, and for my team, now I solved this problem. Yeah. So I need to make -1 on the whole suffix. Yeah, because you remove problem from your suffix sums. Yeah, so whole suffix will be decreased by 1. Again, very technical problem, implementation heavy. It has like 120 lines and they are all kind of important. So you just carefully do this, find. Not the most pleasant problem, I would say, but again, it's a good professional problem. So if you don't know how to do it, just maybe you're just not skilled enough in solving long problems. Again, it's not a skill just to write a lot of code without mistakes. So let's actually read some of your code. I'm curious. What's this? It's Fenwick tree, right? Yeah, it's Fenwick tree. Okay, so you managed to do something like square root by log. That's interesting. We tried to avoid this, so, but okay. So Fenwick is fast enough, so you can fit it. But also you do it without square. Ah, no, you have some b here, so okay. So you just have small number of blocks because it will be multiplied by log. Yes. Okay, and you managed to fit it into time limit. Well, good for you. Good for you. Okay, if it passed all these 300 tests, probably it just works fast enough. That's it. So we had these 8 problems. Thank you again for everyone who solved the contest. Okay, see you next week.